Hello there, fellow scientists. My name is Max, and this is Tea Time with Max. Last 2 weeks, I've been mad. I've been angry and I've been incredibly frustrated. But right now, I'm just disappointed. Why? Because pi is dumb. And I'm gonna tell you exactly why. To the board. So recently, we've been going over waves, oscillations, simple harmonic motions, etc. in my physics course, and the good thing about them is that they are cyclical, they repeat, so we can liken them to a movement on a circle. Let's imagine this is a circle with some radius r, and we want to move, let's say, up to here, with this as being our starting point. One of the ways we can describe this motion is to say that we move in this angle here to, well, anti-clockwise. That's great, cool. What do we use for angles? We use degrees. And how many degrees is there in a full circle? Because if we figure that out, then we know that this angle here would be like, whatever this is, let's say this is 1/6 of a rotation. We take the entirety of a circle divided by 6, we know this angle. So how many degrees is there in a full circle, full rotation? It's 12 degrees. So to get from, what, is not 12 degrees? Oh, yeah, sorry. It's 360 degrees. That's cool, my bad. But why though? Why is it 360 degrees? It could be 12, could be 5, could be whatever. We said it's 360 degrees because it's easy to divide, right? But this is completely arbitrary. It could be any number of degrees. We decided what it was. So perhaps there's a better way of talking about angles, and in fact there is. We use radians to describe the angles on a circle as well. And why? It's because the ratio between a radius and a circumference is the same for every single circle. So we can use that to form a new system for measuring angles. Let's imagine we have an angle like this. So imagine you have the slice of a pizza and we have radius as both arms, and let's say that this distance here is also radius long. We define this angle here as being 1 radian. So 1 radian is an angle that's made by moving 1 radius on the circumference in whichever direction. This is 1 radian. So the next question is, how many of these radians, let's count them, how many of these radians are there in a full rotation? So this is going to be a terrible drawing, but there is approximately 6 and a little bit, 6 and just over a quarter of radians. There's actually about 6.28 radians in 1 full rotation. Cool. Those of you who did A levels would say, oh, we'll probably just spit it out. Oh, there's 2 pi radians within 1 rotation. And here is where the problem starts. We have 1 rotation, so there is 6.28, approximately 6.2831, whatever, radians in a full rotation, and yet we insist on using this. Well, let's think about what pi actually is. So when we have a circle of some diameter, pi is the ratio of the circumference of that circle and that diameter. In fact, the circumference of the diameter of any circle is pi. Okay? Another way to look at it, which is the way Euler looked at it, the famous mathematician, is the ratio between a circumference rather half circumference, and a radius. Cool. This is where we start to have problems, because we defined 1 radian to be 1 radius journey on a circumference, yet we insist on using pi, which is diameter and a circumference, ratio between the circumference and diameter, or the ratio between half circumference and a radius. And we insist on using this to measure that. And we get some really silly results from that. Let's just plot a little table here. On top, I'm gonna say the fraction of a rotation, rather how far are we going, the angle we want to go, and on the bottom, I'm gonna represent that rotation in pi. Okay, so if I want 1 full rotation, okay, so the entire circle, we end up with 2 pi. Okay, cool. What if I want half rotation? 1/2 rotation. Well, we end up with 1 pi. Okay, do you start to see a pattern here? Let's divide it nicely. What if I want 3/7 of a rotation? You know, I can't even be bothered to calculate that, because it takes effort to translate from rotations to pi because of this mismatch here. What if there was a better way? What if we had another constant, which is that? What if we had a constant which is a ratio between a circumference and a radius? Let's call that 2 pi. Let's say that this is 2 pi, and for ease of writing, let's say that this is tau. So tau is the ratio between the circumference and a radius. And let's have a look at what it does to our little table. So, if we have 1 full rotation, how many tau radians is that? 1. If you want half rotation, how many tau radians is that? It's half a tau rotation. What about 3/7 of a rotation? Well, that would be 3/7 of a tau. Do you see how ridiculously simple that is? I can keep going. Let's say 17/19 of a full rotation. How many is that in tau? There's 17/19 tau radians within that rotation. Do you see how simple this is? Those of you who have been, you can say brainwashed. Brainwash is a bit of a strong word, but those of you who have been used to pi, you'll probably be able to calculate this quickly. So that would be like 6/7 pi, I guess. And this would be 34/19 pi. It's nasty. It's nasty. There's no need for this. Well, some of you might argue against that and say pi actually appears in some really important calculations. Like, let's say, for example, the area of a circle. Let's use a different color. The area of a circle is pi r squared. Right? Look, pi is right here. We need pi. Do we know? The actual proof of this is that it was Archimedes, I think, that proven that an area of a circle with some radius r and some circumference c is actually equal to, let me step to this side, it's equal to the area of a triangle, right-angled triangle, with the height of r and the base equal to the circumference. Now, what is the equation for that, for the area of a triangle, it's 1/2 HA, right? Or AH, whichever. We'll multiply and we can move them around, it's fine. Okay, cool. So we know that these are equal because Archimedes, you can look it up. So in our case of this triangle, what will that actually be? That would be 1/2 circumference times the radius, right? This looks like a plus. Circumference times the radius. And if we don't know what the circumference is, well, we can actually link it to here. So circumference will be equal to approximately 6.28 radii, or equal to tau times the radius. So this, in fact, this equation there becomes 1/2 times the circumference, which is actually tau times radius times radius. So in fact, this is 1/2 tau r squared. This is where it comes from. It comes from the area of a triangle. That half there is important. And now, when you see it in this form here, that the area of a circle is 1/2 tau r squared, this tells you something. This shows you the connection. This shows you the actual underlying geometrical truth, as opposed to this monstrosity. All right? But Max, we might say, but Max, hang on a minute. The Euler's identity has pi in it, so pi has to be fundamental, right? So for those of you who don't know, the Euler's identity is e to the pi I plus 1 equals 0. Or, in other words, e to the pi I equals -1. Okay? Look, pi is right here, and Euler wrote it, so it must be fundamental, right? Okay, let's consider this. Let's consider the more general form of this. Because all this is describing is movement on a unit circle in a complex plane. So, what do I actually mean by that? Imagine I have a number line where this here is the real numbers and this here is the imaginary numbers. Okay? So 1 is here, -1 is here, I is here, and -I is here. What this is describing, or rather the more general form of this, which is e to the theta I, theta being the angle, this is describing movement along the unit circle like this. And in fact, the angle here, in radians, tells you where to go, how far to go. You start seeing how pi is there by perhaps an accident. Because this is actually the coordinates. From this we get the coordinates on that unit circle. So this will be some cosine of theta for our real part plus sine theta I for our imaginary part. So pi, being half tau, being half rotation, gets us from here, from the starting point, to here. Hence why e to the power of pi I equals -1. Because it's half rotation right here. So this, in fact, could have easily be e to the tau over 2I equals -1. But in my opinion, a more natural way to look at it is that e to the power of tau I is equal to 1. Why? Because tau radians, 6.28 radians, is describing a full rotation on that circle. So we start at 1, we go tau radians around, and we end up where we started, at 1. This, in fact, should be the true Euler's identity, right here. None of this imposter thing. And if you might think, oh, but the point of Euler's identity is that it connects the 5 most fundamental numbers, which is I, 1, 0, E, and should be tau. This, in fact, is the same as saying 1, well, cos of tau is 1. So 1 plus 0 I. So now we are linking E, tau, I, 1, and 0 in one neat package, the true Euler's identity. Pi is dumb, and I hate it. And this is why. Because tau, or rather any other constant, any other name, anything that gives me the ratio between circumference and radius, this is just so much easier to wrap your head around. And also, it shows you the true nature of the relations in geometry. It's just so much better. Yet we still are stuck with this. And I hate it. So next time I have an exam, the first thing I'm going to do is to write, I can't write in this direction, let tau equal to 2 pi, and then proceed to carry on with tau like a normal person. Right? That's it. That's my rant over. I think I've explained sufficiently that it's time to say pi pi, 2 pi. I'll see you very soon. Bye bye.